Okay, page 4 of the Complex Numbers and Polynomials, Chapter 6, HL. Find exact x and y in the set of real numbers such that 2 times x plus yi equals x minus y I. And remember that the way you do this is you equate the real parts with the imaginary parts, but we just need to simplify it a little bit so that we can equate both parts. And so first we distribute the 2, and then now I think we can equate. So like, for example, the real parts 2x is equal to x, and the imaginary parts 2yi equals negative yi. So 2x equals x, and 2y equals negative 2y equals negative y. So let's set that up. 2x equals x, which is the real part. 2y equals negative y, which is the imaginary part. So the real part says, let's subtract x from both sides. So we basically have x equals 0. And for the other equation, we add y to both sides. We get 3y equals 0. So basically x equals 0 and y equals 0. That's pretty boring. Okay, C looks a little bit more challenging. First, we're going to FOIL the left side. So we'll get first terms multiplied together, give us 3x. The inside and out terms, 3i minus x times iy is going to give us negative ixy. And then multiplying I times negative iy, I'm going to get I squared, which is negative 1, multiplied times negative y is positive y. And that is equal to 1 plus 13i. So let's combine all the real parts here. So this is real, this is real. So the real part is going to be 3x plus y. And the imaginary part is going to be plus 3i minus xyi. So it would be plus 3 minus xyi. And that is equal to 1 plus 13i. So 3x plus y, the real part of the left, is equal to 1, which is the real part of the right. And 3 minus xy, which is the imaginary part of the left, is equal to 13, which is the imaginary part of the right. Now let's continue on. So 3x plus y equals 1. Let's use substitution. We'll solve for y. So y is equal to 1 minus 3x. 3 minus x times y. We're going to substitute in for y 1 minus 3x to eliminate that variable. Then we get 3 minus x plus 3x squared equals 13. Then we subtract 13 from both sides. We get negative 10 minus x plus 3x squared equals 0. And let's reverse the order so that it looks more like a quadratic we're used to solving. Okay, so can we factor this? 3x times x, and then maybe this will be 5, and this will be 2, and this will be negative, and this will be positive. That works, okay? So the solutions are x equals 2, or 3x plus 5 equals 0, 3x equals negative 5, x equals negative 5/3. Okay, and then let's find the y value that corresponds to that. So y equals 1 minus 3x. So y equals 1 minus 3 times 2. That's one of the solutions, okay? It's equal to negative 5. Okay, so that's the solution where x equals 2. So x equals 2 is paired with y equals negative 5. what about x equals negative 5/3? So that would be y equals 1 minus negative 3 times negative 5/3. And that would be equal to 1 plus 5, which is 6. And so that's y equals 6 is paired with x equals negative 5/3. Let's do number 3. The complex number z satisfies this equation. Write z in the form a plus bi, where a and b are real numbers and I equals square root of negative 1. Okay, one thing you have to be careful about is z is a complex number. So like before, we were always assuming that what appeared to be the real part, we could equate. And what appeared to be the complex part, we could also equate. But the problem is that z is a complex number. So 3z is not an orange number. It is partially imaginary, it's partially real. So what we need to do is treat z like a variable, and we need to combine like terms and isolate z. So let's do that. So we have 3z minus, subtract 11 from both, subtract iz from both sides so that we get iz together with 3z. And then we subtract 17i from both sides so that we get the non-z terms like 11 and 17i together. Okay. Then we factor out the z to isolate it. And then we can divide both sides by 3 minus I. So 11 minus 17i divided by 3 minus I. And now we almost have our answer. Now it's like the first type of problem we did, where we're doing a division of complex numbers. So the way you do a division of complex numbers is you just multiply it by the complex conjugate. So let's do that. So the bottom is going to be 3 squared, and I squared is negative 1, and it's minus, so it's going to be positive 1. And the top is going to be 33 would be the first term. Negative 17i squared would be the last term. It would be plus 17. The middle terms are going to be plus 11i. And negative, or 3 times 17 is 51, I think. Is that right? Yeah, 51. So negative 51i. So the top is going to be equal to 50, because 33 plus 17 is 50. 11 minus 51i is negative 40i. Divided by 3 squared plus 1 is 10. 50 divided by 10 is 5. Negative 40 divided by 10 is negative 4. 5 minus 4i. Number 4, express z in the form a plus bi, blah, 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 if z equals, oh my gosh, what a mess. Okay, so looks like the first thing we're going to do, what is the first thing we're going to do? Why don't we try to like simplify the inside before we go off and square this thing? If we square it, it's just going to be a big mess, right? Either we could get a common denominator, yeah, common denominator. So the left term is going to be 4 over 1 plus I. The right term, 7 minus 2i, let's try to multiply it times 1 plus I on top and 1 plus I on the bottom. And then we'll simplify that. So we'll have 4 plus, first term is 7, middle term is negative 2i and 7i, so that'd be plus 5i. Last term would be negative 2i times I, so doing negative 2 times negative 1 is plus 2. And the bottom is just going to be 1 plus I. And let's simplify the top. So we have 4, 7, and 2, we add all those together because they're all real. We get 13 plus 5i. On the bottom, we have 1 plus I. How do we divide? When we divide, what we do is we multiply by the complex conjugate of the denominator, so that we just reduce it to a term that has a real number in the bottom. So the bottom becomes 1, negative 1 times negative 1, which is positive 1, so it would be 1 plus 1 on the bottom. Let me do this to show you just what happens. So 1 times 1 is equal to 1. Negative I times I is equal to negative 1 times negative 1, which is positive 1. And the middle terms, 1i and negative 1i, cancel out. So that's why you get that, okay? Just in case you were losing me every time I did a complex conjugate multiplication. So the bottom's going to be 2, and the top, let's do that. So 13 times 1 is the first two terms multiplied together. 5i times negative I, which are the last terms, I multiply those together, I get 5 times negative 1 times negative 1, which is 5. And the inside term is 5i. And the outside terms, negative I times 13, is negative 13i. So the top is going to be 13 plus 5, which is 18. And then 5 minus 13, which is negative 8i. And the bottom is just going to be divided by 2, so that's equal to 9 minus 4i. Phew, okay, I almost forgot that we're still not done with this problem, because now what we need to do is, all we did up until now is we found out the inside of this thing is equal to 9 minus 4i. Now we want to square 9 minus 4i. So we want to do 9 minus 4i squared. Okay, that's equal to 81. Negative 4i times negative 4i is positive 16i squared, which is negative 16. Negative 4 times 9 is negative 36i, and that's twice, right? Negative 36i, negative 36i. So 81 minus 16 is equal to 65. And 36i minus 36i is, negative 36i minus 36i is minus 72i. Number 5, find the real values of m and n for which 3 times n plus ni equals n minus 2mi minus the quantity 1 minus 2i. First thing I think we want to do is we would like to, these are real values for m and n. So I think this will be a slightly easier problem than the ones we did. We'll see. So we'll have distribute the 3m plus 3ni equals, and now let's try to combine real parts and imaginary parts. So the real part is that, imaginary part is that. So n minus 1, and we can do this because they already said that m and n are real. So when we see n by itself, we know it's real. So n minus 1 is the real part. The imaginary part is negative 2m, and then negative times negative is positive, so positive 2i, so positive 2i. Now we can equate real and imaginary parts, because we know that the m and the n's are real. So 3m equals n minus 1. And we also know that the imaginary parts are real. So we know that 3n equals 2 minus 2m. So let's solve for n. N equals 3m plus 1. And then we'll put it here. 3 times 3m plus 1 equals 2 minus 2m. So 3 times 3 is 9m plus 3 equals 2 minus 2m. Collect the m's, add 2m to both sides, you get 11m. Subtract 3 from both sides, you get negative 1. So m equals negative 1 over 11. N equals 3m plus 1, so n is equal to negative 3 times 1 over 11, negative 1 over 11, plus 1, which is equal to negative 3 elevenths plus 11 elevenths, which is equal to 8 elevenths. Last problem. Express z equals 3i over square root of 2 minus 1i, square root of 2 minus I plus 1 in the form a plus bi. Okay, so, remember that we would like to change this fraction into a fraction that does not have a complex number in the bottom, so we're going to multiply by the complex conjugate. So we're going to have 3i times square root of 2 plus I, which is the complex conjugate, square root of 2 minus I times square root of 2 plus I, plus 1, which is equal to 3i times I is equal to negative 3. 3, and the imaginary part is 3 square root of 2i. And in the denominator, we're going to have square root of 2 squared, which is 2. And we're going to have I times I, which is negative 1. Negative 1 is positive 1. And the outer and inner terms cancel out. And then, we're going to add 1 to that. So let me rewrite everything. So we got negative 3 plus 3 square root of 2i divided by 3. And so each one of these is divided by 3. And then we add 1. Oh, look, negative 3 over 3 is 1. So negative 3 over 3 is 1. It's negative 1. We add it to the 1 that's over here, and we get 0. So, and then we cancel out the 3's here. It simplifies a lot. It simplifies to square root of 2i.